All right, today we're going to be looking at estimating areas under curves. So here's a graph of y equals x squared from 0 to 1. So it's the interval here. We're starting at 0, ending at 1. We're going to try to figure out what's the area of this. Now, this isn't like a triangle where we just have some formula where we could do it. So what we're going to do is estimate this by using a process by going with a shape that we know, which is rectangles. So we're going to estimate this by using some rectangles and finding those areas and then using it to approximate what this area under the curve is. Now you can see from the picture here, if we use the rectangles listed here, we're definitely going to get an area that's somewhat close, but it's definitely going to be an overestimate because we got this extra area outside of the graph that is not going to give us a perfect picture, but does give us an estimate. So we're going to use 4 rectangles here. And what we're going to do is estimate each one by using the right endpoint of each rectangle as the height of the rectangle. So when we're doing this, the first thing we want, well, to find area of a rectangle, we need what's the length of the width times the height. The width here, if we split this into 4 equal rectangles, would each be 1/4 in length, because 1/4 plus 1/4 is a half, plus another fourth is 3/4, plus another one is 1. And a lot of you could probably come up with that in your head. The process of finding this when it maybe isn't so easy is to find this width, which we're going to call our change in x here. We're going to find that by taking the 2 endpoints, which here would be 0 and 1, and we're going to call that a and b. So if you take and subtract those amounts, that would give you the distance all the way across, which here is 1. And we're going to divide that by however many rectangles we're going to split it, where n is the number of rectangles. So putting the numbers in for this one, it would end up being 1 minus 0 divided by 4 rectangles, with 1 and 0 being the endpoints, and we come up with 1/4. So that's the width of each one of these rectangles. That's a fourth, a fourth, a fourth, and 1/4. There are certain times where we'll see problems where these widths might be different lengths, but here they're all the same. Okay, so if we're going to find the total area now, the area of all these, then it's going to be our width, which is 1/4, or here I'll come up with a general equation here. It's going to be our change in x times the height of the first rectangle, which would be our function value at that first rectangle. Okay, so our first rectangle there, if we're going by 1/4 and we're using the right endpoint, the right side of this rectangle is going to have whatever the height is at 1/4. And so this would be the function value at 1/4, because the function value, if you plug in 1/4 to whatever this function is and move it across, that would be the y value, the height. Our next rectangle would again have a width of change in x, and its function value would be if we moved another 1/4. So if we added a fourth and a fourth, now we're at a half. So the height is going to be the function value at a half. Because whatever that y value is at, if we follow 1/2 up, the y value at a half would be the height of this one. If we keep going here, the next one's going to be change in x times the function value. So now if we add another fourth to a half, we're at 3/4. So it's going to be the function value at 3/4. And our last one here would be change in x. And if we add 1/4 onto that one more time, now it's the height at 1. So it'd be f of 1. Okay, so now let's fill in what these are. So our area was going to be 1/4 times. Now we got to figure out what is the function value at 1/4. Well, recall the function that we're looking at here is x squared. This is the graph of right here, y equals x squared, or we could also use function notation, so it would be f of x equals x squared. So if we want to find out what f of x at 1/4 is, we'd want to plug that in. So f at, so this height here, f at 1/4 would equal 1/4 squared. So if we square both the top and bottom value there, 1 squared is 1, 4 squared is 16. So that's the value that we should get for that one. Plus, now we got another 1/4. Now what is f at half? So if we would square a half, 1 squared here is going to be 1, 2 squared would be 4. Plus, now we got another 1/4. If we square the next value, which is 3/4, 3 squared is 9, 4 squared is 16. And then we got our last one here. Again, our width is 1/4. Our height, if we square 1, we can see that value is listed right here. The y value is also going to be 1. 1 squared is 1. All right, so now we got all our heights here. Now we just want to solve that out. What's that going to equal? And that's going to be our approximation here. So A would equal whatever this is. If you're going to type this in your calculator to help you, we could do that. One thing, if all of these heights are the same, or widths are the same of 1/4, we could factor that out and then just add up these heights, and that might be an easier way to type it in your calculator. We could also find this one out by getting a common denominator too. Would also be another way of coming up with this. So if we were to do the common denominator way, looks like the easiest common denominator would be 16. So this would be 1/16 plus 4/16 plus 9/16 plus 1 would be the same as 16/16. So if we add all those up, we get 25 and 5, I think it's 20. Yeah, 20/16. And if we simplify that, I think 4 goes into here 5 times. So it looks like answer we get is, exact answer would be 5/16. If we approximate that, 5/16 looks like approximate answer that we get is about 0.3125. Oh, whoops. I guess looking at this, I added a little bit wrong here. This should be 25 plus 5 should have been 30/16. So if we simplify this one, 4 does not actually quite go into that, so it'd be 15. Looks like we get 15/32. And that would make our final answer here. There we go. So it looks like it's 0.46875. So that would be the estimate of that area. And it's definitely an overestimate here, as we can see those rectangles are all over the curve there. But it gives us an idea, at least, of what that area might be. All right, what we're going to do next now is approximate that same area with rectangles using the left endpoints of the 4 rectangles. So if we did that, now you can see we'll get another estimate with this area here, but this is going to be underestimate because we're leaving some blank space there. But we will at least now, if we do that, have a range of values so that we know that the area would be in between. So on this one, if we're again splitting it into 4 rectangles, we'd use the same values. Our endpoints are 1 and 0, and we're doing 4 rectangles. So each rectangle is going to have a width of 1/4 here. This value is 1/4. This value is 1/4. Each width is 1/4. And we're going to use the heights again. So the heights of all these rectangles. So we're going to have our change in x times the height of that first rectangle. So if we're using left endpoints, we would use the height at the left side. Well, the height at the left side here would be the height at 0. The next one would be the height if we moved over a fourth, which if we move over a fourth, now we're at 1/4. The next one is going to be the height if we moved over another fourth. So if we move over another fourth, we're at 1/2, be the height at 1/2. And then our last one here would be our height if we moved over 1/4 again, which puts us at our height at 3/4. Notice we aren't using the height at 1 because we don't have a rectangle if we're using the left side that starts there. So now if we fill in the values here, this is a fourth. F at 0, it'd be 0 squared. 0 squared is 0. And then we've had these other heights before. When we squared 1/4, we got 1/16. When we squared 1/2, we got 1/4. And when we squared 3/4, we got 9/16. So you could enter that in your calculator to get these. Or again, we could factor out a fourth and add up all the heights. So we'd be adding these values. I'm going to do it without calculator first here, get the exact answer. You want common denominator, so it would be 1/16 plus 4/16 plus 9/16. Hopefully I add them up correctly this time. That would be 14/16. So our area is 1/4 times 14 out of 16. And that's going to simplify. Let's see, 2 goes in here 7 times. So it looks like we get an answer of 7/32, which estimating would be about 0.1875. Okay, so now we know, and we know that this one is an underestimate because we're leaving some blank space in there. All right, so what we've figured out now is a range of values. So yeah, what we figured out is that the two values we got with the left endpoints and the right endpoints, we've now narrowed the area somewhere between these two values. So it's somewhere in that range. Well, what we could keep doing here is we could change. Maybe instead of using just 4 rectangles, we could repeat the process with 8 rectangles. And if we did that, now we would get these two, and you can see that the amount of empty space on the left rectangles becomes a little bit less, and on this one the amount of over area becomes a little bit less too, and now our range here has narrowed a little bit. Well, what if we kept at it? What if we now went to, instead of 8, we went to 10 rectangles or 30 rectangles or 50 rectangles? And you can see that our overage of area becomes less, and on the left side, our estimates, or our amount of white space there, becomes less. So we start narrowing the gap of what that could be. So here's a table of this showing left endpoints and right endpoints. Here's our two estimates at 10 rectangles, 20, they're getting closer. 30, they're getting even closer. Let's jump up. There's 100. Now that's even closer. What if we use 1,000 rectangles? Well, now you can see these numbers are starting to get very close to each other. And if you were to guess, I think looking at that last one, you could probably make a guess that this looks like it's probably approaching a value, if we kept going up to like an infinite number of rectangles, that this looks like it's probably going to 0.33333333 repeating, which means what is our actual area of this one? 1/3. So if we increase the number of rectangles to infinity, we can do that by taking a limit as the number of rectangles goes to infinity. Though the right estimate and the left estimate should end up equaling the same thing of 1/3. So the exact area under that curve, even though it's a curved value, is actually exactly 1/3. And that's what the point of this chapter is going to be, is how we can find area of a curve, or area under a curve. So it's not just like a rectangle or triangle or trapezoid shapes that cut and paste shapes you've looked at before. Now we're looking at curved areas. And what we're going to find is that if you do a limit as the number of rectangles goes to infinity, of all these rectangles, that ends up being the actual area. Now in practice, that's a little hard to find sometimes, because if you had to compute out thousands or millions of rectangles, that's not a very efficient way of doing it. It would take you a very, very long time to add up all those areas. Whereas a computer could do it very fast. And so you could use computers to maybe estimate this, and they can grind out all those calculations very quickly. But we're also going to look at a process later that you can use to do this as well.